Okay, so thanks again everyone for tuning in. So this week we have Adrián Franco-Rubio from Perimeter, who's going to tell us about his work with Shihu and Vidal on continuous tensor networks. Adrián, thank you very much, and take it away.
Okay, thanks a lot. I want to thank you, of course, for having me here. It's a great honor. And as you were saying, I'm going to talk about, so I'm a PhD student here at Perimeter. I'm working under the supervision of Vidal, and I'm going to talk about my work with him and with another PhD student, Chihu, which is currently a preprint in archive, which I've indicated here. So let's begin by trying to place ourselves in the spectrum of physics. We're going to be talking about the renormalization group. As you know, the renormalization group consists of the multi-scale analysis of a physical system, and it of course started in the 60s with the work of Kadanoff, and in the 70s with the work of Wilson, and it is formalized as the RG flow. The RG flow is just the evolution in scale of a set of parameters of a physical theory that under course evolve in a certain way to give you what is the physics and how the physics changes when we change scale. So in particular, the way this is formalized, the framework is that when we perform an RG step, we coarse grain our theory, we get rid of some high energy or short length scale information, and then we obtain an effective theory, and then there's usually a rescaling step that we perform to just be able to compare the theory with the previous one. So for example, if we had that had a UV cutoff, a maximum energy scale, after the coarse graining, because of the effects of it, usually that cutoff is shifted, and we rescale it back to be able to compare the two theories. That's the main idea of the RG flow, and the fixed point of the RG flow, in the particular case of when we are applying it to quantum field theories, are those so-called conformal field theories, which are CFT, scale invariant, and these really important in the past few decades in the study of physics, because one, they describe universality classes of second-order phase transitions, so they allow to describe different the transition between two different phases of matter when it happens in a continuous fashion, in a continuous phase transition. And per se, because these conformal theories, because of their amount of symmetry, they're really they're easier to solve than general quantum field theory. And in fact, they are determined, the quantum field theory, the conformal field theory, by a set of numbers, which are called the conformal data. So, in particular, the implementation of RG flow finds the CFTs. The computational implementation of this, that is given a system. Sorry, is there something?
No,
Are you saying something?
I think it's fine. No.
Okay. Yeah, sorry, I can also not see anyone because the camera is pointing too high. So maybe if you wave at me or something, I might not be able to see it.
Is it better?
Yeah. Great, thanks. Okay, so as I was saying, there's an interesting problem coming from here, which is the computational implementation of an RG flow. If I'm given a system, if I'm given a Hamiltonian for, say, a spin chain, or if I'm given a quantum field theory with a certain set of parameters, can I compute what is the RG flow of this theory? Can I, say, put it in a computer if it is too hard or if it requires a lot of computation, but be able to say how this theory looks like at different scales? And why is this important? Why is this interesting? Well, you would have a series of applications. As I said before, phase classification problems. You can be given a system that depends on parameters, and you want to find out, well, these parameters, what kind of, like, for each value of these parameters, what kind of CFT does this flow to under RG, which is kind of asking what kind of long distance physics does our system have. It would also have implications for computational efficiency, and here I'm showing you're probably going to see later, but because RG is all about coarse graining, sometimes if I have to do a relatively heavy computation, such as computing an expectation value on a lattice on a very large system, if I don't care about the high energy, the short distance aspect of theory, maybe I can coarse grain my theory first, which would make it a system, would considerably reduce the size of the problem just by reducing the system itself. And then I can do my computation in a much more efficient way. Or even if we go to like more fundamental matters in the whole area of research that is holography, RG has become important because, as relatively well known, when the extra direction that appears in holographic systems is usually interpreted as an RG flow. So being able to give a computational implementation of this RG flow, what it's going to do is might provide us with models and with a computational representation of the holographic principle. So in this direction, what do we have right now? Well, it is in the past few years, in the past decades, in fact, tensor networks have arisen as a powerful ways to give an implementation of RG flow, at least in lattice systems. So as a brief introduction, what are tensor networks? Tensor networks are just a set of computational tools. And they have later been found they were introduced merely for computational reasons to reduce the space of parameters that one needs to represent physical objects in a computer. And they later showed that they could provide also some physical insight to the problem. So in tensor networks, which we will see examples later in the talk, I'm just introducing them right now, so don't worry if like you've never seen them and you think this is too fast. We're going to see we need as we go on. But in general, tensor networks, these tools allow for an efficient representation or manipulation of, as I said, certain physical objects, among which from states or statistical functions. This includes the flow of these things. In particular, if we go to quantum states, there's a tensor network called Multiscale Entanglement Renormalization Ansatz, or MERA, which was introduced by Vidal more than a decade ago. And this tensor network is a representation of a quantum state that already encodes the information of its RG flow. So if you're familiar with this kind of tensor networks, in the lower part of it, these indices, these three indices would be the representation of the state, and moving upwards or downwards in the tensor network would just represent coarse-graining or fine-graining in my theory. Side, we have, as I said, statistical partition functions or Euclidean path integrals, which are linked by the classical quantum correspondence of statistical systems, which themselves can be represented as a network of tensors. And this is just an example that I show here of a square lattice that supposedly goes on until infinity in all directions. And in this setting, there's also algorithms that allow us to coarse-grain this theory, that is, obtain the partition function for a theory that is at a higher scale. And the algorithm is the TRG, or Tensor Renormalization Group, which was introduced by Levin and Nave. And then TNR, going to be a focus of attention later, which was introduced later by Glenn Ebley and Guy Vidal. These are just tools that we use to actually implement an RG flow on different kind of systems. And these, because of the nature of tensor networks themselves, they work on the lattice, because it's just a diagrammatic notation, and then a particular bond represents 1 degree of freedom, so we have a discrete set of degrees of freedom. So there's a research program that has arisen lately it's going to be a decade soon, which is that of continuous tensor networks, which is whose aim is that of importing the ideas, the techniques, everything that we have learned from application of tensor networks on the lattice, and see if any of that is useful in the sense of in the realm of quantum field. And in particular, includes the RG flow. Can we use similar strategies to the ones we've used on the lattice, right? An RG flow for quantum theories or wave functionals, that is, of quantum field theory. And in that sense, indeed, there has been progress. Of course, yeah, one of the other consequences of going to the continuum is that your pictures are way less interesting. In 2011, the MERA found a continuous analog. It was found by the group Yuto Hegeman, Verstraete, Verschel, and that was a continuum, which it's called a continuous tensor network because it's no longer represented as a diagram of contractions of tensors, but keeps the same philosophy of what it is an evolution in scale of the system, and how the quantum state of the quantum field theory can be coarse-grained or fine-grained by a unitary evolution in scale. A unitary in the for those who know Mera, in the lattice happens to be unitaries plus isometries, and in the continuum is just unitary. But that doesn't matter. What we're saying just is that for quantum states, we do have an analog in the continuum of the tensor network that provided us with an RG flow. So obviously, by my slide right now, you can guess that the purpose of this talk is just say, if I am given a statistical partition function or a Euclidean path integral in the continuum, can I actually implement some kind of strategy similar to the one that exists on the lattice to provide an RG flow, to provide a computational implementation of the RG flow? And that's the answer that we give in this talk, and the answer we want to give is yes. We don't have still a general algorithm for quantum field theories, but we do have a proposal of a scheme that we know works in the same context that CMERA has also been shown to work, which is that of free theories. And we expect that that will be a point for further increase of our knowledge of how to do this. Okay, that said, I don't know if there's any particular questions, but that was the introduction. And right now, let me just show it's going to be the scheme for the talk. So start by reviewing what is tensor network renormalization, which is the particular algorithm that we aim at generalizing to the continuum, how it works on the lattice. We're going to see that. And then, of course, we'll try to go step by step and say, okay, how do I generalize this particular construction to the continuum, to a quantum field theory? And in particular, we do have an example of a working example, which is for a very simple theory, the Klein-Gordon field, the free scalar. So we're going to see it side by side and go step by step to see how the ideas of TNR are generalized to the continuum and applied to that particular theory. Okay, there are no questions. I will move on to the first part. Okay. So what is the setting for tensor network renormalization? As I said, this is not the first algorithm that provides a tensor network inspired RG flow. On the lattice, there was like the pioneers, Levin and Nave, that I mentioned before. And this one has a particular set of properties that we're going to see that, in a sense, it's really, it's vinculated, it's kind of related to Mera itself, and it's going to give us a handle on how to generalize this thing. But let's go by the basics. As I said, there's this diagrammatic notation for tensors that I assume many people are familiar with, but in case you're not, the only thing you need to know for this talk is in this representation, tensors are just multi-indexed arrays of numbers. So if I have a set of numbers with 4 indices, same like the usual definition of tensor, this is going to be represented by this blob with 4 legs on core index. And then the particular operation of contraction, which is the generalization of say a matrix product, matrices or product of a matrix and a vector, is going to be represented by just the joining of the legs of the tensor that represent the particular index that's being contracted over. So setting for the algorithm, as we said, we're working with partition functions. So I'm going to be using partition function and Euclidean path integral in sort of an equivalent fashion. As I said, because they are linked by these two classical quantum duality. So every time I say one of them, sometimes I will say one or the other, just saying that it's exactly the same thing. So here I could be talking about a discrete partition function or a discretized Euclidean path integral of a particular system. And I represent it in which way? Well, it's represented by a network of tensors that are contracted locally, as you see, and here the bonds just represents the degrees of freedom over. So, is anyone talking?
Yeah.
Sorry, was there a question? Or?
I thought you asked a question if you are following, so I said yes.
Oh, no, sorry. I heard some noises. I thought someone was asking a question. No, sorry. Okay, fine, continue. So as I was saying, the bonds of this tensor network, just think of them as the degrees of freedom. If you're thinking of a partition function, that is a sum over all possible values for degrees of freedom weighted by the energy functional. So, or if you're thinking, say, for a spin model, this would be the bonds represent the degrees of freedom, the spins that we sum over. And then each tensor, the numbers here, they just represent, they contain information of the local Boltzmann weights. That is the value of the functional for those particular values of the spin of the energy function. So that's basically all you need to know about this representation. And then there's an extra factor which will be important later. So we notice that this system in particular, because it's on the lattice, it has a UV cutoff. So there's a lattice space in A that provides an effective shortest length scale or highest energy in our system. Okay, so this is the setting. This is the kind of object that we want to operate on with the algorithm of tensor network renormalization. And the algorithm itself is kind of messy. I show here the picture of the original paper. It has a lot of steps, and many of them are just reaccommodating the tensors and performing some like trivial linear algebra operations. So I'm just going to hide this for now and just focus on the steps that carry the physical meaning. And there's two of them that we want to focus on because those are the two that we're going to generalize later. And in particular, this first one, the insertion of disentanglers and isometries, which I'm going to explain right now, is the one that differentiates this particular method from the previous ones. And the consequence that it had is that this particular method, TNR, does reproduce the correct structure of fixed points in the sense that given a critical field theory, or in this case, a critical system on the lattice, it produces a scaling invariant tensor that contains the correct conformal data. So previously, the algorithms that do not include these disentanglers do fail much more often at critical systems because they don't reach the correct scale invariant tensor. It doesn't really matter. It's just for context in case you were wondering why we chose the algorithm in particular. But yeah, let's move on. Just if you're not familiar with other methods, with tensor renormalization group, or it doesn't really matter. We're just going to try to generalize this particular algorithm. And okay, so as I said, the step that if you want to see it in the general context, it was somewhere around here. Is just the insertion of a series of operators. One of them is a unitary, is the one called U here, which is a unitary, which acting in this particular case on two sides, so on 2 degrees of freedom, which is going to provide a local rearrangement of the degrees of freedom. What's the purpose of that? The purpose of that, and that unitary is chosen variationally by the algorithm precisely to satisfy that, is to decouple the short range entanglement, the short range information, so to say, which is later going to be discarded as we advance. And this discarding is done by the other tensors that we're including, which are isometries. Isometries are just like unitaries, but their target Hilbert space has a smaller dimension. So we're doing just what I said of discarding some correlations, discarding some entanglement that is really short range and is not going to exist in our scaled in a zoomed out version of the model. So that is those two tensors that are chosen variationally in the algorithm, minimizing the corresponding error that we include by discarding the correlations. And as I said, that's a step that was not there originally. In particular, the disentangler, the local rearrangement of the change of basis, local change of basis, was not there in previous algorithms, and this provided a major improvement in the treatment of, say, critical field theory. Okay, and the other step is important, though relatively easy. Yes.
So I have a question. So, like in these previous approaches by Levin and the collaborator, did you have like just the isometry but no disentangler, or
yeah, you could represent it like that in a sense. The system was based on the singular value decomposition, which can be thought of as putting two isometries and conjugating your higher order tensors, your higher dimensional tensors, by isometries that reduce their dimensionality. And those isometries are chosen, like the SVD already it's a variational problem that aims at minimizing the norm of the error caused by the truncation, but the truncation does not have information of what information is important in a sense of what information is short range and what information is long range.
And this you organized by introducing disentangler.
Sorry?
And this you include into the problem by introducing the disentangler.
Yeah, so the disentangler allows for a change of basis there in such a fashion that later the isometries are able. It's kind of a, so the whole idea is something called entanglement renormalization, which was already seen in the context of quantum states, and it like the basic idea is that if you one coarse grains naively by taking SVDs, reducing dimensionality without any particular criterion, just by isometries, it might go well in non-critical systems because at some point you run out of correlations. But in critical systems, these short-range correlations, which we are not discarding properly, they accumulate. So in the end, they drive your algorithm relatively crazy because whenever you're coarse-graining, the error done by keeping the error produced by keeping all those short-range correlations that you should be decoupling from the system, it accumulates over time, and over a certain range of scales, it becomes too high.
Okay, thanks.
Okay. So as I was saying, that's a particular step of the algorithm, and it's kind of the core of the algorithm. After that, the rest of those steps are just like linear algebra manipulations to be able to leave the lattice as it was before. And the last step of those is one that I will want to call attention to, which is simply the fact that whenever we are coarse graining, we end up with one tensor for each 4 tensors that we had before in the case of the square lattice. So what happens in the end is that we end up with a lattice that has twice the lattice parameter, which is relatively natural since we coarse grain the system. So the last step of the first iteration of each RG step, each iteration of the algorithm, is just a simple rescaling, which on the lattice it doesn't really matter much. It's just how you draw your lattice, but just taking into account that each degree of freedom should now be thought of being exactly at the same distance that we were in the previous lattice, so that the UV cutoff stays invariant. Because that way you have a means of comparing the two theories. So again, if you got kind of lost with the algorithm, just the thing that you have to remember from this is that this algorithm performs some series of operations on the lattice, and it ends up implementing an RG flow in the space of tensors, in the sense that before we had a particular tensor, and if you go back to the setting, this particular tensor, which was repeated many times, and it contained the information of the theory, the local Boltzmann weights at that scale. And after we perform a series of local operations, which include rearrangements of degrees of freedom, we end up with a different tensor, which represents the theory at a higher scale. And that can be iterated, and so on and so forth. So why is this important? Because once we apply that, we see that each phase of a particular thinking, and we're going to be thinking of the example of, say, an Ising model, which is relatively simple system that has 2 phases. Each phase is going to flow to a particular fixed scale invariant tensor. That is that after a series of iterations of the algorithm, we're going to see that it doesn't change anymore, which in the RG flow means we have converged to the corresponding fixed point, which can be a conformal field theory for critical systems. It can be a trivial CFT or a massive fixed point if we start in a system that was non-critical. And this evolution of this convergence, so to say, which of course, after a certain number of iterations, numerical errors are going to accumulate, and you in the end up with something that is not useful, but for a really long time, you do observe convergence. And this convergence is the one that is going to give us, for example, information about the phase diagram of the system. And in particular, if we are sitting at a phase transition point, that is if the system is critical, we're going to be able to return formal data. Remember, the CFT was characterized by a particular set of numbers, which are called in this particular case scaling dimensions, conformal spins, OP coefficients. Well, so scaling dimensions and conformal spins, for example, are going to be relatively easy to obtain from the tensor, from the coarse grain tensor, from the fixed point tensor. So in that sense, the RG flow succeeds at giving us the full structure of the phase space of the system. In particular, if we see the example here of an Ising model, relatively a simple classical Ising model at a certain temperature, which has 2 phases, the order phase at low temperatures disorder phase at high temperatures, and a critical temperature in the middle, in the transition. Well, each of these phases converge to different tensors, and we observe that indeed from each of these tensors we can deduce what kind of phase it was. The tensors of the order, they are non-critical, they flow to massive fixed points, and the one for a critical system does contain information of the conformal data. And in particular, if you're curious because of the C2 order symmetry, well, there's an actual relationship between these two tensors, in the sense that the one that has the two copies of the symmetry breaking is like a direct sum of two copies of the one that is disordered, but that doesn't matter right now for our purposes. It's just saying that indeed this algorithm on the lattice provides the correct structure of fixed points for the RG flow. Okay, so that's mostly what I wanted to say about tensor network renormalization on the lattice. You see, sorry for repeating myself, but it's just an algorithm meant to coarse-grain partition functions, or the path integral, discretize Euclidean path integrals. And what it does is to, first, well, a series of steps, which mainly the two important ones are rearranging locally degrees of freedom, following a certain variation principle, and rescaling the lattice to keep the lattice in the same, to keep the same shape of the lattice that we used to have before. And we see that it's creating an RG flow. So the goal now is, okay, how do we do this in the continuum? In the continuum, the setting, of course, is going to change. And we're going to have Euclidean path integral, or partition function again. Let me stick with the name of Euclidean path integral, in which we are just integrating over all field configurations with a certain weight, which is an exponential of a Euclidean action. And, oops, sorry, here there's something that shouldn't be seen yet, but forget about the middle part. I did a PowerPoint blunder. What I just wanted to say before we go to the next one is this Euclidean path integral. Each degree of freedom, which before lived on the bounds of the tensor network, is just going to be the values of the field at a particular point. And then the information of the theory itself is the thing that before used to be the tensors, the numbers in the tensors. Now it's going to be, of course, the action that is weighted each field configuration. And what I wanted to mention is in order for us to have a UV cutoff, in order for us to have like a reference that is going to move when it's when we're performing the RG, and also in more general case, maybe assuming that our theory is not well behaved at the UV, we're going to introduce a UV cutoff ourselves. Is there a question? No. Okay. So as I was saying, what we're going to do is we're going to introduce a UV cutoff ourselves. And the way we choose to do it is heavily inspired in the continuous MERA. So as I said, if you have heard of the continuous MERA, which was the continuous tensor network for wave functionals instead of partition functions, don't worry about it, but just saying for those who know it, that this way is heavily inspired in that, and that is the introduction of smeared fields. So smeared fields, which have been conspicuously here and voluntarily during the previous slide, they are just, as I said, smeared versions of the original fields. We just produce another field configuration from the original one by weighting it, by making the convolution with a particular profile. We're going to respect the symmetries of the theory. In particular because, and this is something that, sorry, I forgot to say before, one of the main rationales, one of the main motivations for moving all this to the tensor network business to the continuum is that in the continuum we can try to respect the full Poincaré, or in this case, rotational signature, rotational symmetry of the theory, while in the lattice, if we just went by going to a discretization and apply tensor networks, lattice tensor networks, we would find out that, of course, our symmetry is heavily reduced because it's quotiented by the corresponding lattice. So we end up with a very reduced symmetry group. So I was just saying that, sorry for the slight diversion, to justify that we're going to choose this profile, this smearing profile for our fields to be a function just of the distance, to just keep rotational symmetry and translational symmetry. And this is just going to be, imagine a Gaussian profile, for example, that is going to have a characteristic length scale, which acts as the as the length scale that we had in the lattice, which acts on our continuum theory in the same way that the lattice parameter acted on the lattice as a UV cutoff, as a definite characteristic length scale below which the theory behaves more trivially. And then we can just define as mirrored action as the action evaluated on the fields. This is exactly the same thing as I was saying before that happens in the continuous mirror, in which the fields are also, after the evolution, are replaced with mirrored fields. Okay. And as I said, this can be translated again back to the, this is a picture of what is happening, more or less. It's imagining in 2D, the Euclidean path integral, and our mirrored fields have a certain file that is characterized by some length scale 1 over lambda. I'm using the usual notation in which lambda is a momentum cutoff, so the associated length scale would be 1 over lambda, but just think of it as width of the Gaussian, which is great. And as I promised, we are going to be seeing step by step how this setting, how this works in the case of an example of the Klein-Gordon theory. So here it is. This is the Lagrangian for a Klein-Gordon theory. I've included a mass. Later we'll get rid of that when we speak about CFTs. But for the time, we're going to keep it. And this Lagrangian for the Klein-Gordon field, we can regularize. We can regularize the action in the same way I was saying before by introducing smearing. So we replace the fields by fields that are no longer local but have a certain length scale. And if we compute, say, with this new action, if we compute the 2-point function, then what we observe is indeed that the behavior along distances, which we want to leave in like unaltered, because we're only like adding a UV cutoff to the theory. The behavior of the correlator along distances just goes with the logarithm that is characteristic of the free boson, the 2-point function of the free boson. And just whenever we go to length scale that are of the order or smaller than the cutoff, that's when the divergence, that was the logarithmic divergence that we have here, disappears, and we just go to a constant. And there is a delta function, the on-site delta function, which itself is kind of a remnant of what would be a product partition function. If you think of a lattice model, that's just the on-site interaction. This is equivalent to the same thing. It's kind of telling you that this is a hybrid between the actual theory along distances and a trivial theory that only has self interactions localized at a point at short distances. Okay, so this is just the setting. You want to, sorry?
How do you
yes.
How do you calculate explicitly this correlation function?
Sorry, can you speak a little bit louder?
How do you calculate explicitly the correlation function?
Oh, the correlation function is just the usual way of if you write your, this is still quadratic in the field. It does have a, like we've added the smearing, but it's still quadratic. So if you wanted the usual way, you write this in Fourier variables. The Fourier variables, you will have phi of k, phi minus k, and then some propagator in Fourier space. Sorry, some inverse of the propagator, which you would then invert to get the propagator. And then you perform the Fourier transform of that. You have to subtract a constant to make it Fourier transformable in the numerical way if you want. And the constant gives you the delta, and then the function that you end up with, as you remove the constant and a particular term that gives you the long distance behavior, what remains is an integrable function that you can Fourier transform numerically.
Okay, so
and then you obtain this.
In the path integral language, what you do is like you don't change the path integral measure, but like what you change is
exactly, yeah,
by the action.
yeah. We only replace the action. In principle, this mirroring, you can kind of argue that you expect the path integral measure not to be changed, because if you rewrite it in momentum space, the smearing is just multiplying by a function. So the convolution that happens in real space, in momentum space, is just going to be the product of the two transforms. So if you write the path integral in momentum space, your measure is going to be just multiplied by an infinite product of constants that whenever you're taking expectation values is going to cancel. So just the only change that happens is in the action, and then you use the standard Gaussian integration techniques. Okay. So if there's no more questions, about the setting, we move to the actual algorithm. So after all these ramblings of mine, do not forget what was our actual goal, which was implementing the RG flow, implementing a scale transformation or a coarse-graining transformation, better said, at the level of Euclidean path integrals. And these we're going to say, remember that previously in the lattice, we were doing local rearrangements of degrees of freedom. So what we're going to do is precisely define now in the continuum, so infinitesimally, a transformation of the field that is going to play the same value. And again, here, in case people are familiar with continuous Mera, this is also heavily inspired in the continuous Mera framework. So this transformation of the fields, this field definition, is just going to alter infinitesimally each field by a particular delta of phi, the field configuration, which is obtained by acting a generator on the field, just as any infinitesimal evolution. And in particular, we have split the generator here into parts. So we're going to explain now why we do this splitting. And that is because, not forgetting the lattice, each of these parts corresponds to a particular one of the two steps that we singled out as like the main points of the algorithm of the lattice. And I'm actually going to start in reverse because the easiest one is just scaling. Remember that one of the steps was just keep the lattice cutoff constant. So we had to perform a scale transformation, and scale transformation in the case of the quantum theory is just implemented by this of scaling operator, which has rescaled the space, then if necessary adds a particular scaling dimension to the field. So that's just the L part of the generator, and it's kind of fixed. It's just like the matter content of the theory is going to tell you what shape this has. And the other more important part of the generator, the other part, if you remember, of the algorithm, was this local rearrangement of degrees of freedom or local change of degrees of freedom. And this we're going to just implement by a certain operator called K that we're calling Disentangling or Disentangling. And this is again inspired on the continuous Mera. Why Disentangler? Because we're thinking of removing the short range entanglement, removing the short range correlations so that we can coarse grain efficiently. And this we're going to leave kind of completely free. We know that it's going to be quasi-local because it's going to be, by quasi-local, I mean operating at the length scale that is that of the UV cutoff. So it's not going to be a operator. It's going to be just it's going to have some kind of profile. And we're going to, apart from that, leave it quite free. We're going to allow it in principle to change in scale, the way that if you are familiar with the Mera or well, in general, that an RG transformation need not be constant as we change scale, the way we implement the transformation itself. So this parameter S here is just a scale. And we're going to say that this particular generator on the fields just acts according to a certain function.
Okay, I have
yes?
The question is the transformation of the field represented unitarily? And the second one is the scaling transformation that you invoke here in the language of Chimera, this non-relativistic scaling transformation?
Okay, so first question, is it implemented unitarily? I'm not sure. We would like to, I mean, it depends. Now the meaning of unitary is kind of blurred because we are talking about transformations just in the field configurations. If you trivially make a Hilbert space of the field configurations by just writing a basis in field configuration is an element of the basis, then which is going to be non-separable and horrible and everything. But in principle, yeah, you can think of this as a linear map, as basically any function is going to mapping and configuration to another field configuration, and that except for like, I think you can expect it to be unitary in most cases, but in general, the meaning of the unitarity itself that we had before when we had like Hilbert spaces assigned to particular bonds is kind of lost in a way. Because here we have, or at least we haven't been able to give a very precise meaning of that. It would of course be very interesting to say, indeed we're keeping some unitarity in the sense that we are keeping some norm, or we're making sure that we are not changing some particular norm of the action, norm of the tensor or something. But yeah, that's in principle. If you want to implement these variations, finally, which is the end goal that we are not at yet, but we are aiming at, then of course you could try to find some proxy for unitarity, which would be defining some norm for the action, say in the space of parameters that you're flowing in, and trying to keep that norm fixed.
Okay.
But yeah, there's a straightforward way in which I can say that this is a unitary transformation, as clearly as I could say that the previous disentanglers were unitaries. And the second question, sorry?
No, go ahead.
And the second question, I think you were asking me if this is the non-relativistic from the non-relativistic scaling operator.
Yeah.
Could it be? Yeah. Yeah, it looks so that L that in the continuous mirror for the free boson, this L is sometimes called because of the way it acts, the non-relativistic scaling operator. Yeah, in principle, you're going to fix between those, they only differ on the well, actually, I mean, in a sense, they differ. It's called non-relativistic because it gives different values of the scaling dimension, phi and pi. So it breaks phi being the field operator and pi being the conjugate momentum, which means that treating differently space and time directions. Here we are working in a Lagrangian formalism in which there is no conjugate momentum. We're just speaking of the field. This is just the field configuration that goes in the path integral, and also we're Euclidean signature, so we are not Lorentz invariant. We're Euclidean rotational invariant, but in principle we're trying to keep that symmetry. So it's just the scaling operator in 2 dimensions that scales everything isotropically. And I said I didn't say well. In principle, you would like K of S, the operator. Well, in principle, you are going to impose that in most cases that your scaling your coarse-graining transformation is also isotropic, which in the lattice it was only partially isotropic because, of course, it's a lattice. But here you would like it to be fully isotropic. That's why I skipped here the term of dependence on the gradient, and I only included dependence on, say, the Laplacian and other scaling variant constructions, scaling variant terms. Rotation invariant terms of phi. Was that satisfactory as an answer? Okay. So yeah, thanks for the question. And okay, so trying to retake the thread, we have defined here just a transformation in the space of field configurations that we have, and we have convenience and for easier analogy with the lattice, we have separated the contribution to this transformation that comes from scaling, the contribution just trivially scaling lattice, and the contribution which is going to be at the core of the algorithm, which is the disentangling, which does the actual identification of short distance correlations and removal of those, which is just the air of the local rearrangement of freedom that we had on the lattice. And yeah, so just to make more precise this thing that I'm saying all the time of the lattice continuum analogy, let me be insistent and repeat one more time. Lattice spacing, we had a UV cutoff, it has become a smearing length. So this is independent, it's just a matter of the setting, not of the algorithm itself, that we have introduced a cutoff in the theory by smearing. And then, of course, the tensors become part. The tensor at a scale S is going to be represented. It's going to have the same information as the Lagrangian at a scale S. And we are already including the smearing. I mean, this is just telling you that these tensors are at a certain distance from each other, so they include the information of some kind of local environment. And the transformations that we included, the unitary transformation that rearranged the degrees of freedom, was now going to become the disentangler, this operator case, which in principle we're going to allow to evolve, to change depending on scale. And then this just following along, applying this infinitesimal operator, generating a flow with it, generate a flow for the partition function. It's just going to be, as I said, applying the corresponding the corresponding L and the corresponding K, which might here at corresponding scale, to generate a flow for the action. And then the corresponding partition function for that action would be the partition function that represents your system at a certain scale. Okay, so this is all very general, very abstract. It's not providing any particular example. So let's do that again. Let's go back to the particular example that we had. And of course, as I said, we still don't have a general algorithm for how to find K, in the same way that the analogous part in K in continuous Mera is still not fully variational. We don't, it's not understood how to do it, except for the case of free theories. So we are going to follow the case of free theories, and we're going to propose an ansatz for the disentangler that is going to be linear. It's going to be linear in the field, and then one of the few things that we can do that is quasi-local and linear in the fields is again another smearing. A different smearing, before we had a certain profile that we call mu, if I may remind you. This is just the smearing of, this is the profile of the operator, and it's going to a profile, a field configuration phi, and then smear it according to a certain profile that again, it's rotational invariant and my dependence scale. So this is our case that we want to apply to the free boson. Again, it's a free theory, it's linear, quadratic, linear, depends if you're speaking of the action or the equation of motion. And this is our ansatz for the disentangler. And of course, it's inspired on the continuous Mera. So now is when we are going to also include an extra piece of information that we know, and that is that if we set the mass to 0 in our free boson, what we get is a conformal of the theory, which should be a fixed point of the RG flow. The same way that on the lattice, when we put a critical Hamiltonian, we know that should be a fixed point of the RG flow that should be scale invariant. So when we set the mass to 0, we're going to say, okay, so what we want to impose, what would a good disentangler satisfy? It should leave the action invariant. Should the RG flow generated when applied to a particular conformal field theory, well, to any conformal field theory, to the particular one, should be treated. So that's why I've added these stars here. That just mean fixed point. I think it's relatively usual notation for fixed point. And this is just saying, okay, the infinitesimal action of my RG flow on my particular example that I'm studying, that is a CFT, is it leaves it unchanged. And of course, because that should be valid at all scales, what we have also done is getting rid of the scale dependence of the operator, of the generator, because in principle, that's precisely the meaning of scale invariant. So we do that with all the setting, with the previous action that we had, the smeared action for the free boson, and with this particular ansatz for a disentangler. What we find is that indeed that this condition can be satisfied. And we find that the fixed point condition this is horrible grammar, sorry, implies just a relationship between mu, that if I may remind you, is just the way that we chose, the way that we chose to regularize our fields. So it's just a matter of how we are, what's the setting that we're working in, what's the particular theory, the particular UV regularization of a free boson theory that we're using. Sorry, let me go back again, forward. And G, that as we said before, was just the parameter, the actual scaling operator, disentangling operator. So this is just telling you, and it's written in momentum space because it's easier, but it doesn't really matter. What it's telling you is, okay, for any UV regularization that you give me of the theory, I can give you a correct disentangler that is going to implement an RG flow that leaves your theory constant. And then in particular, you have to include another sanity requirements or like consistency requirements, which would be that these profiles are themselves not too non-local, that you have a smearing of your theory that is not catastrophic, that doesn't make it horribly non-local, and that your disentangler, also acts in a kind of quasi-local way without having very non-decaying tails. So that's an extra condition that we need to impose. And then when you that, when you impose the condition of fixed point and the condition of the function involved in the problem being quasi-local, being decent functions, so to say, without aiming to offend any other functions, we can find, and we give in the paper if you're interested to read it, a particular realization of a set of a particular regularization of the CFT, given by a certain mu, a particular entangler, disentangler, whose profile is actually a Gaussian, with again some delta, that means it has a residual local term, such that the regularized free boson is a fixed point of our algorithm. So we have the full construction working. We have kind of back engineered it because we have already imposed what the target was. That was to get the free boson to be a fixed point of the algorithm. But we have the proof of principle that this scheme can work and can produce a fixed point. And before, and let me announce that it's going to come later before I move on, that what we get as well is that this particular implementation respects the CFT conformal data. So for any particular regularization, this is what it's meaning here, that I give you of a cutoff, of a regularization that I give you of the theory, sorry. There exists a correct CTNR scheme, a correct renormalization operation that leaves these conformal data as the ones that they should be, the ones corresponding to the free boson CFT. But that we'll see later. Okay, so this was just to flash the properties of the functions, that they are adequately local, exponentially decaying, or Gaussianly decaying, etc. Okay, so this is just to understand, in case it was not clear, what the formations are doing, why we split it in that way, to give you a mental picture. So I've just represented my system in a one-dimensional way, and it's just like the particular smearing profile of two field insertions, call it like that. So this would be the mu. So what happens, why do we have these two parts in the coarse-graining transformation? In the lattice, it's relatively obvious because we ended up with a lattice that is twice as big, so we had to remove that. What's the rationale here? Well, if you think of applying the scaling transformation first, it's just easier to think. What happens is that we coarse grain, we zoom out again, in this case, trivially because we're just applying the scale transformation. And what is going to happen is that is going to change the cutoff in our theory. That's the cutoff of the lattice spacing changing. So what K does is nothing more and nothing less than that cutoff to its particular, to its original value. So this thing that I wanted to stress here is that indeed the same way that we had in the lattice algorithm, the net effect of the whole algorithm, of each step, and in this case of the sum of the two generators, is to leave the cutoff invariant, so that like the whole RG flow, we can at any point stop it and compare its theory to all the other theories in the RG flow. Which is in this case necessary given that we need a fixed point. But I mean, fixed point is stronger than just having the same cutoff. And in particular, if we add a mass, if we now forget about the condition that we had the mass equals 0, we can, I mean, in principle, the entangler could change. The entangler, sorry, I'm changing entangler, disentangler, just think of it with a minus sign going up or going down. So the expected flow would be once we add a mass, that's a relevant transformation, relevant deformation that takes it to a massive fixed point. And indeed, if we just naively plug in the same RT flow generators that we had, we see that the scale dependent action becomes indeed something that, well, the CFT part is invariant because it's the same one that left the CFT alone invariant, and then the massive term just gets a particular weighting of an exponential that is driving you to the infinite mass fixed point. So that's just naively, it needn't have worked in principle to just apply the same generators that we had, but it does provide a reasonable answer. And as I was saying before, as I already made the announcement, we can recover the correct conformal data for a particular fixed point. In particular, the fixed point that is the CFT of the free boson. You can recover the scaling dimensions of the free boson. You can recover the conformal spins. And this, in case, I don't want to enter too much into the interpretation of these equations, but in case you recognize them, these are just saying that the scaling dimensions and conformal spins, please, sorry, don't mistake the scaling dimension with the Laplacian. I forgot to change this to nabla square. So the scaling dimensions and conformal spins, which are conformal data, and they are the common eigenvalues, sorry, the eigenvalues associated to common eigenvectors of the scaling operator and the rotation generator. These are recovered exactly from our construction, but of course the eigenvectors change. The eigenvectors are no longer the well-known scaling original CFT scaling operators, I don't know, derivatives of phi and all that, but they are a smeared version of those. They are a quasi-local version of those because, of course, our implementation of the scale transformations is now quasi-local. It's no longer local. So yeah, moral of the story, we have built a particular instance of a CTNR scheme, of a continuous tensor network renormalization scheme that satisfies this desirable condition. That once we choose, and there we have a certain degree of freedom, once we choose a particular implementation of the UV regularization of the theory, we can find a generator, an L plus K, that is going to be leave that the free theory invariant, the free massless theory invariant as a CFT, and it's going to still encode the corresponding the right properties as a fixed point of the RG flow, which are the conformal data. Okay, so with that, let me conclude. I think I'm almost done with my time. So, and you're going to tell me that I repeat myself too much, but hopefully that's useful in this case. As I said, tensor networks have been already in the lattice for more than a decade to work in realizing the RG flow in systems on the lattice. And then more recently, there were more developments that allowed us to go not only to gapped phases, but also to gapless critical models and obtain a correct phase diagram structure. And what we have accomplished here is proposing a general scheme for a similar interpretation of the RG flow, a similar implementation, sorry, of the RG flow now in the continuum, which is morally based in all that we learned in the lattice. Of course, that is not yet, it's what we are aiming for. It's not yet a fully variational algorithm, which would be the most desirable, but we have shown that there exists at least an example, a proof of principle example, which is the free boson. And the same happens for the continuous mirror, for example, that is so far only understood for free theories, in which the correct fixed point behavior is retrieved. In particular, we can get correct conformal data and the behavior of the theories as we should expect, and there exists a way to implement that. Of course, in the near future, or in the far future, if you're more or less optimistic or pessimistic, we would like to develop this fully developed into a variational algorithm that can, given a particular action, of course, you will need a regularizing scheme to be able to give a cutoff and then perform RG flow on that. So with that, I would like to conclude. Thank you for your attention. Here's the archive number in case you're interested in learning more about this. And thank you a lot.
Thank you. Any final questions?
Oh, I do have one, or actually maybe more than one, two. So one question is like in the original TNR story, the paper claiming TNR yields MERA.
Yes.
And
that is some.
Well, I mean, my question is like that over here, like you guys develop like tensor network normalization for a pattern table for a field theory for a free boson. So can you see in these considerations like sort of like layers of CMERA or something similar to CMERA appearing? So that's my first question. And the second question is, and maybe you said it, but I just didn't get it. But my impression was that what you do like works for any way of UV regularizing your theory. So like you just pick some sort of like a local enough view, and that fits for you like this variational, like these parameters in your coarse-graining transformations. And in this sense, I didn't see there like a taste of variational class, in the sense that you didn't do like any sort of variational optimization, or at least I didn't see it. So could you please comment on this as well?
Okay, let me see if I remember everything. Yeah, the first question, indeed, very good question. We've of course been thinking about that because as he was pointing out, when you apply, there's an intimate connection that I think I mentioned like at some point very briefly in the talk between the TNR algorithm that coarse-grains partition functions and the mera that coarse-grains states, and that is as follows. If you start with a state that is defined by a partition function by a path with a boundary, and you coarse-grain by TNR, this of course is going to work in the same way in the bulk of the partition function, and then it has some like adapted. You cannot apply it fully, only partially on the boundary. And what can be seen, this is just I'm saying, of course, I know that, you know this, but for other people that might not know it, what you observe is that the TNR algorithm, TNR steps, end up building a mera representation of the quantum state. So we expected to try to find something similar here, and it's not that clear. And the reason for that is something that I mentioned before, that when we are presenting our continuous TNR algorithm, we've chosen to regularize our theory in order to preserve symmetries, to regularize it in a rotation invariant way. What does that mean? That means that our theory is non-local in both what would be space and Euclidean time direction, which means there's not an easy way to, once you make a cut, once you put a sharp boundary in your field theory, to define a Hilbert space there that would be the Hilbert space of a quantum field theory. So in principle, that kind of disqualifies the possibility of getting a quantum wave functional basically from these construct path integrals such as the ones that we are discussing. Of course, you can just say that in principle I don't care about the rotational invariance in the path integral, and then you can take some anisotropic limit in which this smearing profile becomes basically a smearing profile in some kind of spatial foliation of your path integral, and then in the end you would be able to, in the limiting case of this becoming just a one-dimensional smearing, you will be able to find a quantum state, a wave functional on the boundary, and that, of course, yeah, would resemble a continuous mirror. But in the fully general case, because we kind of like held the preservation of symmetries to a really high esteem, we don't find a Hilbert space in the boundary, so it's harder. That was one thing, and the second thing was about sorry. So you asked
like TNR,
variational
answers, and over here, like I sort of like got confused because I didn't see like a variational optimization. So I'm just wondering if
you didn't see a variational character. Indeed, I mean, in the proposal. So as I said, we're aiming for a variational class. So far, we don't have general proposals. So, well, or better, so we have a very general one, which is this. The disentangler should be some function, some quasi-local function that is, of course, a super general variational class of possible operators that can give you an RG flow. Sorry. And in the particular case of free theories, of linear theories, we did reduce it quite drastically to things that are linear in the fields. And this is still a variational class, which, again, our variational principle here was not as much a variational an optimization such as demanding the fixed point. So I agree that indeed this is not a variational scheme that if you give me right now an action, I'm going to be able to apply it. If you give me some like general random action, but we would expect it in the future to have some kind of variational of more better definite variational class. Yeah.
Okay.
I don't know if this answers the question.
That clears things up. Thank you.
Yeah. So as I said, yeah, the example here was mainly to prove that indeed it's possible, and it's also possible to preserve the structure of a fixed point and the behavior of a very easy example, such as the phase space of the free boson with only the mass as parameter. It can be preserved. It can be realized, better said.
Okay. So if there are no more questions, let's thank Adrián again.
Thanks.
Thank you.